The National Electrical Code requires an adequately sized grounding electrode system to provide a low impedance path to earth for fault currents and lightning strikes. The NEC provides specific requirements for the minimum size and types of grounding electrodes, as well as supplemental electrodes. Observing undersized grounding electrodes on large service installations is concerning and can pose a significant safety hazard and violate code requirements. The use of plastic water service pipes has become more common in recent years. However, metal water pipes are still considered the preferred grounding electrode due to their conductivity and low impedance. When metal water pipes are no longer present, other grounding electrodes must be used to meet code requirements. Consider an example of an 800 amp service with a single number 4 U for ground and a number 6 ground rod, which is inadequate. According to Table 250.66 of the NEC, the minimum grounding conductor size for a 400 amp service is number 2 AWG. Therefore, the grounding electrode conductor for an 800 amp service should be at least number 0 AWG. NEC 250.52 A3 states that concrete encased electrode shall not be smaller than number 4 AWG. However, this does not preclude the use of larger grounding electrodes as required by Table 250.66. NEC 250.66 clearly states that the grounding electrode conductor shall not be less than the sizes specified in the table. This implies that other forms of grounding electrodes, such as U for grounds or grounding plates, can be used as supplemental electrodes but cannot be substituted for the minimum requirements of Table 250.66. If the transformer loses its neutral, or a large surge or lightning strikes the building, an undersized grounding electrode system may not be able to safely dissipate the fault current. This can lead to equipment damage, fire, or even injury or death. It is crucial that grounding electrode systems be properly sized and installed to ensure the safety of electrical installations. Electrical inspectors should carefully review grounding systems for compliance with the NEC and consider the potential risks associated with undersized grounding electrodes. The use of larger grounding electrodes, such as 3/0 AWD grounding rings or U for grounds, is recommended for large service installations to provide adequate protection against electrical hazards. To further elaborate on grounding electrode systems and their critical role in electrical safety, consider the following points. Grounding electrode systems serve as the primary connection between an electrical system and the earth. This connection provides a low impedance path for fault currents, which are unintended currents that can occur due to insulation failures or other electrical faults. A properly sized and installed grounding electrode system ensures that these fault currents are safely conducted to the earth, minimizing the risk of electrical shock, fire, and equipment damage. The NEC specifies the types of grounding electrodes that are permitted for use in electrical systems. These include metal water pipes, concrete encased electrodes, ground rings, and ground rods. The NEC also provides specific requirements for the size, material, and installation of these electrodes. Metal water pipes, when available, are often considered the preferred grounding electrode due to their extensive contact with the earth and their inherent conductivity. However, as plastic water pipes become more prevalent, alternative grounding electrodes must be used to meet code requirements. Concrete encased electrodes, also known as U for grounds, are commonly used in new construction. These electrodes consist of a length of bare copper conductor encased in concrete near the bottom of a foundation or footing. U for grounds provide a reliable and effective grounding path, especially in areas with poor soil conductivity. Ground rings are another type of grounding electrode that can be used in electrical systems. These electrodes consist of a continuous loop of bare copper conductor buried in the earth around the perimeter of a building or structure. Ground rings provide a low impedance grounding path and are particularly effective in areas with high soil resistivity. Ground rods are the most common type of grounding electrode used in electrical systems. These electrodes consist of metal rods driven into the earth to provide a connection to ground. Ground rods are relatively inexpensive and easy to install, making them a popular choice for many applications. However, Ground rods may not be as effective as other types of grounding electrodes in areas with poor soil conductivity. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides a table 250.66, that specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. It is important to note that the grounding electrode conductor must be sized according to this table, regardless of the type of grounding electrode used. In addition to the primary grounding electrode, supplemental grounding electrodes are often required to enhance the effectiveness of the grounding system. Supplemental grounding electrodes can include additional ground rods, ground rings, or other types of electrodes. The NEC provides specific requirements for the installation of supplemental grounding electrodes. One common requirement is that supplemental grounding electrodes must be bonded together to form a single grounding electrode system. This bonding ensures that all grounding electrodes are at the same potential, minimizing the risk of voltage differences that could create electrical hazards. Undersized grounding electrodes can have serious consequences for the safety of electrical systems. If a grounding electrode is too small, it may not be able to safely conduct fault currents to the earth. This can result in elevated voltage levels on metal parts of equipment, increasing the risk of electrical shock. Undersized grounding electrodes can also increase the risk of fire. When fault currents are not properly grounded, they can flow through unintended paths, such as building steel or metal conduit. This can cause these materials to overheat, potentially igniting nearby combustible materials. In addition to the safety hazards, undersized grounding electrodes can also damage electrical equipment. When fault currents are not properly grounded, they can damage sensitive electronic components such as computers and control systems. This can result in costly repairs and downtime. It is essential for electrical inspectors to carefully review grounding systems for compliance with the NEC. Inspectors should verify that the grounding electrode is of the correct type and size, and that it is properly installed. Inspectors should also check for any signs of damage or corrosion to the grounding electrode system. If any deficiencies are found, they should be corrected immediately to ensure the safety of the electrical system. In summary, grounding electrode systems are a critical component of electrical safety. Properly sized and installed grounding electrodes provide a low impedance path for fault currents, minimizing the risk of electrical shock, fire, and equipment damage. The electrical inspector should carefully review grounding systems for compliance with the NEC and take appropriate action to correct any deficiencies. The selection and implementation of appropriate grounding electrode systems are crucial for ensuring the safety and reliability of electrical installations in various types of buildings, including apartment complexes. A comprehensive understanding of the NEC requirements, coupled with practical considerations of soil conditions and available grounding methods, is essential for electrical engineers, contractors, and inspectors. In the context of apartment complexes, where multiple dwelling units are served by a common electrical system, the importance of a robust grounding system is amplified. The potential for ground faults and electrical hazards is greater due to the increased number of appliances, electrical devices, and wiring connections. Therefore, the grounding system must be designed and installed to effectively mitigate these risks and protect the occupants of the building. When evaluating the grounding system for an apartment complex, several factors must be taken into account. Firstly, the size of the service entrance conductors must be determined. This will dictate the minimum size of the grounding electrode conductor, as specified in NEC Table 250.66. Secondly, the type of grounding electrode to be used must be selected. The choice of grounding electrode will depend on factors such as soil conditions, the availability of a metal water pipe, and the presence of concrete encased electrodes. Thirdly, the need for supplemental grounding electrodes must be assessed. Supplemental grounding electrodes may be required to enhance the effectiveness of the grounding system, particularly in areas with poor soil conductivity. In the specific example of the apartment complex with two 800 amp services per building, the grounding system should be carefully designed to meet the requirements of the NEC. As previously mentioned, a single number 4U for ground and a number 6 ground rod are inadequate for the size of service. The minimum grounding electrode conductor size for an 800 amp service is number 0 AWG, according to table 250.66. Therefore, the grounding system should include a grounding electrode conductor of at least number 0 AWG connected to a suitable grounding electrode. A 3/0 grounding ring or 3/0U for ground would be appropriate choices for this application. These electrodes provide a large surface area in contact with the earth, ensuring a low impedance grounding path. The use of a grounding plate is generally not recommended in areas with corrosive soils, as it can corrode over time and lose its effectiveness. In addition to the primary grounding electrode, supplemental grounding electrodes should be installed to further enhance the grounding system. These supplemental electrodes can include additional ground rods or ground rings bonded together to form a single grounding electrode system. It is important to ensure that all grounding connections are made properly using approved connectors and techniques. Loose or corroded connections can significantly increase the impedance of the grounding system, reducing its effectiveness. Regular inspections and maintenance of the grounding system are essential to ensure its continued performance. Grounding connections should be checked for tightness and corrosion, and any damaged or deteriorated component should be replaced promptly. In conclusion, a properly designed and installed grounding system is crucial for the safety and reliability of electrical installations in apartment complexes. The grounding system must meet the requirements of the NEC and be tailored to the specific characteristics of the building and its surrounding environment. Regular inspections and maintenance are essential to ensure the continued performance of the grounding system and protect the occupants of the building from electrical hazards. The significance of grounding systems in electrical safety cannot be overstated, particularly in complex electrical installations like apartment complexes. These systems are not merely an afterthought or a code requirement, but rather a fundamental component of the overall electrical infrastructure that protects people and property from the dangers of electrical faults. A well-designed and maintained grounding system provides a low impedance path for fault currents, allowing them to flow safely back to the source and trip the circuit breaker or fuse, interrupting the flow of electricity and preventing potential hazards. Without an effective grounding system, fault currents can take unintended paths through conductive materials such as metal pipes, building structures, or even people, leading to electrical shock, fire, or equipment damage. The NEC provides a comprehensive set of rules and guidelines for the design and installation of grounding systems, covering various aspects such as the types of grounding electrodes, the size of grounding conductors, and the methods of bonding and grounding equipment. These requirements are based on years of experience and research, and are intended to ensure the safety and reliability of electrical installations. However, simply complying with the NEC requirements is not enough. A thorough understanding of the principles of grounding and bonding is essential for electrical engineers, contractors, and inspectors to design and install effective grounding systems that meet the specific needs of each installation. In addition to the NEC requirements, there are also several industry standards and best practices that can be followed to enhance the performance of grounding systems. These include recommendations for the selection of grounding electrodes, the installation of grounding conductors, and the testing and maintenance of grounding systems. One important aspect of grounding system design is the selection of appropriate grounding electrodes. Choice of grounding electrode will depend on factors such as soil conditions, the availability of a metal water pipe, and the presence of concrete encased electrodes. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or to use a ground-enhancing material to improve the conductivity of the soil. Another important consideration is the size of the grounding conductors. The NEC specifies the minimum size of grounding conductors based on the size of the service entrance conductors, but it may be necessary to use larger conductors in some cases to ensure a low impedance grounding path. The installation of grounding conductors is also critical. Grounding conductors must be installed in a neat and workmanlike manner and must be protected from physical damage. All grounding connections must be made using approved connectors and techniques, and must be properly tightened to ensure a good electrical connection. Regular testing and maintenance of grounding systems are essential to ensure their continued performance. Grounding connections should be checked for tightness and corrosion, and any damaged or deteriorated components should be replaced promptly. Ground resistance measurements should be taken periodically to verify the effectiveness of the grounding system. In apartment complexes, the grounding system must be designed to protect all of the dwelling units from electrical hazards. This typically involves installing a grounding electrode system that is common to all of the units, and then bonding the grounding system to the metal parts of the building structure and the electrical equipment in each unit. The grounding system must also be designed to protect the common areas of the apartment complex, such as hallways, stairwells, and laundry rooms. This may involve installing additional grounding electrodes or using a separate grounding system for the common areas. In conclusion, grounding systems are a critical component of electrical safety and must be designed, installed, and maintained properly to protect people and property from electrical hazards. A thorough understanding of the principles of grounding and bonding, as well as compliance with the NEC requirements and industry best practices, is essential for ensuring the safety and reliability of electrical installations in apartment complexes and other types of buildings. Remember to prioritize safety and consult with qualified electrical professionals to ensure that your grounding system is properly designed and installed.